This is a very interesting and beautiful equation with floor functions. We want to find all pairs of xy with x and y being positive such that this equation holds. Now, note that this notation, the floor of r for any real number r, basically is the greatest integer less than or equal to r. Okay, so that's the definition of the floor function. Now, this problem might look pretty challenging. However, I encourage you to pause the video and try to figure out the solution on your own. It's actually a very elegant and beautiful one. Done? All right, let's get started. So, firstly, you want to figure out what makes the problem hard. In this case, when you look at the problem, what makes this problem look intimidating? The floor functions, right? How are we supposed to deal with them? So, we might want to consider a simpler version of the problem in which the floor functions won't make the problem any harder. But what case is that? Well, that case is when x and y are both integers, right? When they're both integers, then the floor function is just overkill because the floor of an integer is just itself. So, when they're both integers, then this equation simply becomes x squared plus y squared all squared is equal to 2x to the 4 plus y to the 4. And now we can expand and distribute. So over here we get x to the 4 plus 2x squared y squared plus x to the 4, not x to the 4, y to the 4. So y to the 4, this is equal to 2x to the 4 plus 2y to the 4. And now we can rearrange the equation. We can rearrange this equation into x to the 4, and then plus y to the 4, and then minus 2x squared y squared is equal to 0. And would you look at that? This side is just a binomial squared. It's just equal to x squared minus y squared is equal to, all squared, right? And then this is equal to 0. Now, because of this, we can deduce that x squared is equal to y squared, right? Because this inner part also has to be 0. And therefore, taking the square root, we get x is equal to y. We can take the square root like this because they're both positive, so it must mean that x is equal to y. So under this case, when x and y are both integers, then we have already deduced a solution. The solutions in the pairs x, y, one solution would be n for any positive integer n. Now that we've dealt with that case, it's time to ask the obvious question. What if at least one of x and y is not an integer? Well, this is actually the bulk of the work. This is the most challenging part of this entire problem. And remember that time when I asked you to pause the video and try to figure out a solution on your own? Well, if you have some sort of insight, then now is the time to pause and try to figure out the solution. Because, I promise you, the solution is a very elegant and beautiful one. I would not want to spoil it to you if you can figure it out on your own. Done? Let's continue then. Firstly, over here, we really only have two options. We can either derive the remaining solutions and then prove that they are the only ones, or we can try to prove that no other solutions exist. Well, what would be really helpful is if we could derive some sort of condition which limits the number of solutions. Because in that case, either A, we have some sort of restriction which allows us to get the remaining solutions, or B, prove that no other solutions exist. But how do we derive such a constraining condition? Well, notice that over here, we have an expression with floor of x squared and floor of y squared. And I would really like to relate this expression with another expression containing only x squared and y squared. Now, I know that x to the 4 and y to the 4, they are the squares of these two terms. However, I just want an expression with these two terms alone, not them squared or to some other power. And why am I doing this in the first place? Well, that's because one very trivial fact is that the floor of x is always smaller or equal to x, right? And also, the floor of y is always smaller or equal to y. And because they're both positive, we can square both sides. And over here, we can basically derive the fact that floor of x squared plus floor of y squared is always smaller or equal to x squared plus y squared. Obvious, however, this could be extremely useful. Because let's say that we derive some sort of condition that states that floor of x squared plus floor of y squared is also greater or equal to x squared plus y squared. If we can derive something like this, for example, then this would be super, super helpful because they're both smaller or equal to and greater or equal to, then they have to be equal, right? So if we can derive some sort of constraining condition like this, then that would be key to us. Okay, so the plan is to relate this expression with something containing only x squared and y squared. However, this expression is pretty annoying. Thankfully, it's equal to this side, and this side is much easier to deal with. I mean, these two are just the squares of x squared and y squared, so it should be much easier to deal with. Still, how do we relate them to x squared and y squared? Well, we can actually use a very famous inequality that is super helpful in relating expressions with square terms. And this inequality is the quadratic mean arithmetic mean inequality. This is abbreviated as QMAM inequality. It states that if you have two positive real numbers x1 and x2, then it follows that the square root of x1 squared plus x2 squared over 2 is greater or equal to x1 plus x2 over 2. This is the QMAM inequality. And by the way, this actually extends way beyond two terms, but we only need the one where we have two terms. So this is sufficient. Now, if we were to take x1 to be x squared and x2 to be y squared, then notice that the QMAM inequality will give us that the square root of x to the 4 plus y to the 4 over 2 is greater or equal to x squared plus y squared and divided by 2, right? Now, notice that we have our desired expressions. We have x to the 4 and y to the 4, and we have x squared and y squared. We're able to get a desired relationship between the two variables. All we have to do is do some isolation. In particular, we want to isolate so that we can have 2 times x to the 4 plus y to the 4 on one side. Well, a good first step over here is to square both sides, right? Get rid of the square root. So if you square both sides, you would get x to the 4 plus y to the 4 over 2 is greater or equal to x squared plus y squared and all squared over 4. And over here, to get 2 times x to the 4 plus y to the 4, you just have to multiply both sides by 4, right? And this side will become our desired expression of 2 times x to the 4 plus y to the 4. And 4 and 4 over here, they cancel away. And therefore, we have something that is very beautiful. Because now we can confidently say that this thing over here, well, by the QMAM inequality, it's equal, well, it's not equal to, it's always greater or equal to this. Now notice that this over here is equal to this, right? So we can just make that substitution. So it's going to be, and now because both sides are positive, we can take the square root, no problem. So we have floor of x squared plus floor of y squared is greater or equal to x squared plus y squared. Now, do you see what we have? We have something majestic. And the reason is because earlier we saw that floor of x squared plus floor of y squared must also be smaller or equal to x squared and y squared, right? So, combining these two inequalities together, it must be greater or equal to and smaller or equal to? Well, the only possibility is that floor of x squared plus floor of y squared is equal to x squared plus y squared. But when can this happen? Well, this can only happen when x and y are both integers. And the reason is pretty obvious. If they are not both integers, then at least one of these will be greater than, these two. So obviously, they both have to be integers in that case. So to achieve equality, both x and y must be integers. But we proved earlier that if they're both integers, then this is the only solution. So indeed, this is the only solution to this equation. So that's how we can derive a constraining condition to limit our solutions. And we were able to prove that no other solutions exist. Now, notice that the main idea of a problem like this is to first consider a simple case. You want to first make the problem easier. In this case, when you consider the case when x and y are both integers, then this side is not scary at all, right? You got a solution. And then you can work on some sort of rigorous proof as to why there might be no other solutions. Oftentimes, a lot of hard problems like this, especially ones involving find all whatever satisfying whatever, these kind of problems will often have very simple answers, very simple solutions, and they come from very simple cases. But the work to prove that they're the only ones is challenging. Anyway, that's going to be it for this video. I hope you enjoyed it. If you found it interesting, then please do consider dropping a like and subscribing. Thank you very much. Bye.